Hello friends, I welcome you all to the next lecture of the JC eConnect series of online lecture. We are into module 4 and we have started to discuss the concept of moment of inertia. In the previous lectures, we have covered the definition of moment of inertia, understood the concept of moment of inertia. Further, we have understood the concept of radius of gyration. Then we have dealt with parallel axis theorem and perpendicular axis theorem. So moving ahead, we will find the moment of inertia of some important figures using the applications learnt previously. So first, let us start with the rectangle. So in the figure, we have a rectangle of breadth B and depth D. Then we have marked the centroidal axis because we know where the CG of the rectangle lies directly. That is, XX axis and YY axis represent the centroidal axis of the rectangle. Then for analysis, let us consider a small elementary strip of depth dy, which is at a distance y from the centroidal axis. So the area of this strip will be b into dy, and as the distance of the strip is y units from the horizontal centroidal axis, the moment of inertia of this strip about xx axis is nothing but area into square of the perpendicular distance. Therefore, moment of inertia of the strip about xx axis is b into dy into y square. This previously we have discussed how we get moment of inertia. It is the product of the area multiplied by the square of the distance. So here the moment of inertia of the elemental strip about xx axis is b into dy, which is the area of the strip, and y square, where y is the distance of that elemental area from centroidal x axis. Then further, if we want to find moment of whole figure about xx axis, the whole figure consists of such various number of elemental strips. Okay, we can divide this rectangle into n number of rectangle strips. That means it is integration. So integration of b into dy into y square. So the concept goes easy. First we are finding the moment of inertia of one strip. Then when we consider the entire figure, this figure is made up of such number of elemental strips, hence we have to take the integration. Then how to fix the limits of integration? Here our centroidal axis is at the center itself, means if we go up from the centroidal axis, our limit will be maximum plus d by 2, whereas if we come below the centroidal axis, our lower limit will be minus d by 2. Okay, understand this properly. As we are moving from the horizontal centroidal axis, our limits will be, upper limit will be plus d by 2 and the lower limit will be minus d by 2. Therefore, when we go ahead with integration, we get b into bracket integration of y square dy, we get it as y cube by 3 with the upper limit as d by 2 and the lower limit as minus d by 2. So when we substitute the upper and the lower limit and solve, we get ix is equal to bd cube by 12. Okay, so the moment of inertia of a rectangular figure about its horizontal centroidal axis is nothing but ix is equal to bd cube by 12. Similarly, when we find moment of inertia about y axis, okay, we will get the solution as db cube by 12. So these both are our required moment of inertias of the rectangle about the centroidal axis. Okay, we need to find moment of inertia of a figure about centroidal axis, which we have found out. So next, moving on, let us take one more common figure, which is a triangle. Now in this case, I have a triangle ABC. the total area is divided again into an elemental strip of width B1, which is at a distance y from the base, and the remaining height is d minus y, where d is the total depth of the triangle. You can take the term h or you can take the term d, it doesn't matter. So what we have done here, we have a triangle ABC, the base is b and the depth is d. So you can take it as depth or height, small h also if you take, it is fine. Then we take an elementary strip of depth dy and width b1. We consider that strip as rectangular, and that strip lies at a distance y or a depth y from the base AB. Then the remaining portion of the triangle is d minus y, because the total depth is d. Therefore, by using principle of similar triangles, now the similar thing we have done in centroid derivation also. So if you have understood that, here you should be able to pick up a bit faster. Using the principle of similar triangles, b1 divided by b is equal to d minus y divided by d, where d is the total depth. Okay, please show it in the figure when you make the notes. D is the total depth. From that we get b1 is equal to d minus y into b divided by d. This is the application of similar triangles. So now what will be the area of the strip? Area of the strip is b1 into dy, and we have found out the b1 value, which we have to substitute. So area of the strip is equal to b1 is d minus y into b divided by d into dy, which is the depth of the strip. Therefore, moment of inertia of the strip about the base AB. Okay, we are taking the base AB as the reference in this case. How will you find the moment of inertia? Area of the strip multiplied by the square of the perpendicular distance. Now, the perpendicular distance in this case of the strip with respect to the base is AB. A question will arise why we are not taking centroidal axis. At the end of the derivation, I will answer that question if it has arisen. Okay, we are initially finding the moment of inertia about the base AB. Okay, so first let us find that, then I will tell how will we convert that to the centroid. So then, expanding the bracket and multiplying, this is basic multiplication, we get by square into dy minus by cube into dy divided by d as moment of inertia of the strip about AB, which is the base. Here we are not doing anything, we are just multiplying the terms inside. Okay, we are just multiplying the terms inside and keeping it. So further, next step is now moment of inertia of the whole area about AB. So whole area will be made up of such number of strips. Okay, so it is integration. Now integration of what? The previous terms which we have got. Okay, two terms are there in the previous equation. Integration of 0 to d. Now why here we are taking 0 to d? Because our axis about which we are finding the moment of inertia is not the centroidal axis, but it's about the base. Okay, AB base we are taking as a reference and finding the moment of inertia. Therefore, we are submitting the limits as 0 to d. At AB, depth of the triangle is 0. Whereas as we go higher and reach the apex point of the triangle, that is C, the depth of the triangle becomes small d. Hence our limits here in this case are 0 to d. Therefore, integrating, substituting the limits, we get IAB is equal to BD cube by 12. Okay, this is moment of inertia of the triangle about which axis? About the base. Now let us find the moment of inertia of the same triangle about centroidal axis. At what distance does the centroid lie from the base? Yes, h by 3 or d by 3. Okay, the centroid lies at h by 3 or d by 3. H and d, whatever you take, it is right. So now How will be the centroidal axis with respect to base? Yes, the centroidal axis will be parallel with respect to the base. So which theorem we can use here? Yes, we can apply parallel axis theorem to find the moment of inertia about centroidal axis XX with respect to the figure. So what we have done here is, as we have a well defined base, that is AB, we found the moment of inertia of the triangular figure about the base. Then as the axis lies at a distance of h by 3 or say d by 3 from the base, and that centroidal axis will be parallel to AB, we will use the parallel axis theorem application and directly find Ixx. Now initially itself, if you go to find Ixx directly, the limits will be h by 3 and 2h by 3 or d by 3 and 2d by 3. Then integration process becomes a bit complicated. So easily we can find the moment of inertia about the base, apply parallel axis theorem and find moment of inertia about the xx axis. So this is the important concept which you have to understand. So going further, moment of inertia about xx axis. Where does the xx axis lie? Mark in the triangle. At what height? D by 3 or 1/3 of d. As we are dealing here in the term d, we can use the term d by 3 or 1/3 of d. So using which theorem? Using parallel axis theorem. What does the parallel axis theorem say? IAB is equal to Ix plus Ay square. Okay. Moment of inertia about any axis parallel to the centroidal axis can be obtained by this relationship as per your parallel axis theorem, which we have gone through in the previous video. Now here we have already IAB. What we need to find? Ix. So shifting that term Ay square on the other side, it gets the negative sign. IAB is what? BD cube by 12. Then capital A is the area, which is what? Half base into depth of the triangle. Then what will be y square? Now this is interesting. What is y when we apply parallel axis theorem? It is the perpendicular distance between the centroidal axis and the other axis. Now here our other axis is base AB, centroidal axis is xx. So for a triangle, where is the centroid? At a distance of d by 3 or 1/3 of d from the base. Therefore in this case, y is equal to 1/3 of d. This is a very important point which you should note. Okay, y in this case is 1/3 of d whole square. So when we solve, we get the answer as BD cube by 36. So if we are solving for a triangle and we want to find moment of inertia, the procedure is, first we find the moment of inertia about the base, then apply the parallel axis theorem, and then we will get the moment of inertia about the horizontal axis as BD cube by 36. So if you perform similar exercise, okay, if you perform similar exercise about y axis, you will get the moment of inertia as dB cube by 6. Okay, BD cube for x axis and dB cube for y axis. Okay, so this is how we find out moment of inertia of a rectangle, of a triangle about its centroidal axis xx and yy. Okay, so even if that last line is not written, it won't matter much. If you get the derivation up to BD cube by 36, it is more than sufficient. Hopefully these two derivations are clear. In the next class we will complete 2 more derivations, up to where you will have the portion for the internals. Thank you.